Good afternoon, everybody. Now session 2 we have started, and we have now with us that Professor Bhaskar Choubey. It's a distinguished professor and distinguished fellow from Germany, and he has lots of experience in the entire world basically, and he is the chair now in analog circuit and image sensor, Siegen University from 2018 onwards. Then he has worked in different university, and he was in long experience in University of Oxford, and then he was also worked in Glasgow University. And after that, and there are lots of visiting position he has, like Marie Curie fellow and in Italy, and he was a visiting associate professor in Kazakhstan, international visiting fellow also in University of Sydney, Australia, and he was also a Microsoft Inspire lecture he is giving in South Africa, and he was a guest scientist in also in Max Planck Institute and Germany. You know, the honorary lecture he is giving in also in our India this Neris. So, and he has completed their education from basically in NIT Warangal now, and then after that he has completed their Doctor of Philosophy in University of Oxford. He has long experience, and he has long awards and honors is there, and he has a IEEE Sensor Counseling Early Career Achievement Award he has received. Raymond Davis Scholarship he has received. D.H. Thomas Award he has received. I cannot say all the award and honors, and he has different IEEE journal. He was an associate editor and different member also. So it is the very proud to be, I can say that in this FDP he has agreed to give this invited talk to us, and it's a boost for our FDP. And thank you, sir. Thank you very much, sir, for your presence in the FDP. Thank you. And this is, you know, that CMOS image sensor is the one of the hot topics, and somehow we have got, sir, and I think next 1.5 hours we'll see that very good input from the sir, because due to this online platform also we are getting this opportunity to get something by sitting in the office or sitting in the home, and that and personally also he's a very nice person, and also technically I have told he's a very honorary professor. So I think we can start, sir, and thank you very much again for your presence in this FDP.
Thanks, Dr. Maiti. With no ado, I will start sharing my screen. Good morning to all of you, or good afternoon to all of you in India. I will try this lecture to be at least less boring than India-England cricket match, so that you are not completely losing track with reality. So I hope you can all see my screen. Now, while we are having this presentation, this will be an open for all presentations. If you want to ask questions, please raise hand, and Dr. Maiti would enable you to ask questions in between, so we don't have to wait till the end. Right, here we go. We are going to talk about CMOS image sensors. More importantly, we are going to answer these two very simple questions. What is the history of selfie? And when can we have a gazillion megapixel camera? Now, all of you guys have bought cameras in the market. At least you have bought a mobile phone in the market which has got a camera. And we are always interested in more number of pixels. So we just try to measure our wealth in terms of if I have a 10 megapixel camera, or somebody has 20, 30, 40, 100, and so on and so forth. So that's one aspect of the camera world, or the image sensors world. And the other aspect is we are interested in taking pictures of ourselves. So is this a new phenomenon? If so, why it had led to this movement, and how does technology help or hinder this whole concept of selfie taking? So let's start about the gazillion megapixel. If I ask all of you how many pixels do you have, I'm sure some of you at least would be able to check your mobile phones or your computer screens. If you're on a computer screen, it's fairly poor webcam, but if you're having a good mobile phone, it would have a good number of pixels, right from low-end ones to about 2 to 3 megapixel to higher ones at almost 100 megapixel. And if you're buying some of the newer mobile phones, you might even have more than one camera. You may have 3 or 4 cameras in the back side. You might have 1 or 2 cameras on the front side. So all this sounds very good. The question is, how many pixels do you need? And that is an interesting question, because the marketing guy who's trying to sell us a mobile phone or sell us a camera almost always tells that more the number of pixels, better your camera is going to be. So let's try to answer this question. How many megapixels do we actually need? But before we answer that question, we need to ask, what do we do of the images which we take? Most of the time, we either see it on our mobile phones or see them on a computer screen, send them to a friend using any of the internet-based protocols, WhatsApp, HTTP, mail, etc. Now, if you might remember, the screen resolution is only about 1920 by 2000, so that's barely 2 megapixels. Your phone resolution is even lower. The number of pixels on the display of your phone are even lower than that. So why are we taking 48 megapixel image if we want to see them on a 2 megapixel screen? Now that's one limitation. Actually, the hardest thing you can do with an image is do this. You can print the image. Some of the old people might still remember we used to print the postcard size images. But if you're trying to print the image, the size of a postcard size is about 6 into 4 inches. And even if you have got a very good printer, you're going to print about 300 dots per inch. Better than that, the human eye can't resolve. Human eye can't even resolve 100 dots per inch. So for a very good quality picture, you need 2.16 million. If you are more ambitious and you want to print it on an A4 size paper, my apologies, that's not an A, then it's an 8 by 6 inch paper. So you are essentially requiring 3.2 megapixel max. Some of the older folks might remember 3.2 megapixel was a generation of cameras we had in mobile phones as well as in digital SLR or digital cameras. We used to have the digital handheld cameras. So what you actually need is you only need 3.2 megapixel. You don't need more than that. So that's the one end of the spectrum. We have pushed the number of megapixel way beyond we need. We are doing something more important than this. Don't worry, I'm not going to end the lecture saying the technology has been done, go home now. There's the other end of the spectrum. Whom do you compare it with? How do you compare that you have the best, optimum, most brilliant camera in the world? So let's try to compare it with one thing we know which is there, which is the human eye. That's a camera, it's a very good camera. So if you take one of the state-of-the-art digital cameras, say Canon 5DS, it has got about 50 megapixel, the area is about 860 millimeters square. So that's a DSLR sensor. It's about a year, about 2 year old, so still fairly modern for DSLR world. And that's way more than what your mobile phones have. Your human eye has about 100 megapixel rod, 5 megapixel cones. So way more than our cameras have. But more importantly, unlike our cameras which are flat, this is actually it uses a curved structure. So you can see the lens here, the film is a curved film. By using a curved film, it uses a very, very simple lens. Whereas when we do imaging, if you're having a very complex imager, you're using complex lenses or multiple lenses. Our mobile phone cameras are actually flat and we don't use very good lenses, and that's why the image quality is still not terribly great. Let's try to compare it to the human eye. How are we different? How are our digital cameras different to human eye? So human eye starts not only takes picture, it starts processing, and it does quite a lot of processing. You can start figuring out if there is a tiger coming. Well, if there's a motion happening in your scene or not. You can't identify which type of motion, but something is moving. And when we evolved as human beings and we used to live in forests, if something is moving behind us, that's quite important. If there's a tiger, we need to run. So the human eye tells that information even before the picture goes to your brain. That's not done in digital cameras. Digital cameras just record the picture and that's the end of it. The number of pixels is 120 megapixels in human eye. We are still stuck at about 2 to 50 megapixel. We have very good dynamic range. If it's very bright or very dark, our human eye still works. Digital camera, not so much. The power requirement of human eye is terribly low. I mean, the amount of power which we give to any neural processing is way lower than the amount of power our batteries, our mobile phones need. When we eat normal food, that does not give very high amount of horsepower compared to the amount of batteries we provide. We don't know about the noise, the color reproduction of human eye is excellent. Digital cameras, they're improving, they're not yet there yet. If I go down further to the optical assembly, to the task here, the human eye is a very simple optical lens. It's just one single lens, and when it goes wrong, we put another lens in forms of glasses and we are done. Digital camera, you either need a very complex lens or you produce a very poor image. Well, the manufacturing time, that's a bit of a joke. Well, the human eye needs about 9 months of manufacturing time plus about 5 years of learning time. When a child is born, it doesn't see very well. It certainly doesn't see color. The digital cameras take about 3 to 4 months. But more important is the development time. Human eye has evolved over millions of years. We are about 20 years old in digital cameras world. So we are not yet there, but the quality of performance is improving. But we still have a much better camera to compare ourselves to. So that's all about why we need more well, where we are in terms of number of megapixels, excuse me. Got a bit of cold. Now let's talk about the application. Now we have quite a lot of cameras with us. Most of the time we end up taking pictures of ourselves. We take our selfies in some notation or other. And this is very much an animal-related trait. Even if you look at chimpanzees or baboons, they try looking at themselves. We all love looking at ourselves. We think we are the best-looking person. The history of imaging is actually quite old. So, I mean, just the sheer ability to take record. And we have always liked taking images or recording images in one form or the other as a representation of ourselves, but also as a representation of our society, our culture, and so on and so forth. So we started, so these are some of the oldest caves, the first X-ray image. If you now talk about where we were for about 50,000 years of human evolution, when we started painting things on caves to digital cameras, the first digital camera actually came in 1975. So this was a Kodak piece. And look at the brilliant size of the camera. It has got a tape recorder or a tape on one side. You might see this is the cassette player which we used to have till a few days ago. It weighed 4 kilograms. It can only take black and white images. It stored the images on a digital cassette. Its resolution was 0.01 megapixel. But more importantly, it took 23 seconds to take a picture. So for 23 seconds, you have to stand still while the camera is taking a picture of you. Fast forward, in 1988, we came with something like this. This was the Canon RC250. In 1988, this is after I was born, so it's not too... It was called Ion in Europe. It costed $500 US, so I guess in Indian currency that would be 25,000 rupees. But if you wanted everything, battery, floppy drives, computer hard disks, it will cost you $1,000 or something like 60 to 75,000 rupees just for a camera. This is the camera there. You needed a floppy drive to store your images. If you move even forward, in 1990s, we already has digital, Logitech's making their Dicam Model 1, which was 0.09 megapixel. And this was still costing about $1,000. And now you see the pace at which things are flowing. So within a year, we went from 0.09 megapixel to about 1.3 megapixel. And within 4 years, We're still selling it at a very high price, $750 but we have got things which can take 640 by 480 images, and we have got a 1 megabyte flash memory. So with 1 megabyte flash memory, our camera could store about 32 poor quality images. This is within 4 years, and we are only about 15 years since the days when we were just taking 8 pictures in a plane to a days when your mobile phones can store thousands of pictures. What happened to the first camera phone? Now, the first camera phone was a Samsung SCHV200. It could take about 20 photos, and it was at 0.35 megapixel. But what was more interesting was it could only take picture, it could not send. And this is where Sharp's first phone, JSH04, becomes very interesting. Not only you can take a picture, image quality was 0.11 megapixel, you could actually send a picture. Now at that time, people were, we are talking about 2000, people are still thinking, why would you want to take a really small picture of yours and send it to someone? So I picked up a news item on BBC and it said something really interesting. It talked about taking pictures with your phone. So this is the really tiny phone which you can take a picture. Now I know when you read news item online, there's a comment section where people place comments as to good or bad of the image. And this was a very good comment which I saw there. Infinite use for the teenagers, not entirely sure why anyone would need, what the rest of the world will do with a camera phone. It's just 2000. Fast forward 13 years and the word of the year is selfie. That has become so prominent, that is the predominant aspect of camera industry. And the back camera of a mobile phone is getting even better. Now actually the selfie saved my industry, because by that time we had made a very good back camera and we had said, we don't need to go any forward, the world is done, let's go and do something else. But now you want the front camera to be very good. So the front camera, iPhone 4 introduced the front camera, and then the flip phone had a 0.3 megapixel camera. But right now we are putting even the front camera is coming to 15 megapixel and so on and so forth. So the power dissipation and the energy consumption of this is becoming quite critical. I know I've taken about 13 minutes talking about history of the camera world to get you excited as to how quickly this field has moved. But if you, I believe there's a question, is there? Oh no, it's just a good afternoon, sorry. If you look at, when I talked about the history of selfie, if you now look at what's this whole idea of taking our own picture, it started way early. There were painters who used to put themselves in an image. So that's Lemanias, where you have got ladies in the waiting and the painter has painted himself while he's painting somebody else. There is Botticelli putting himself in a big series of painters. And then you have got Van Gogh, Rembrandt, and all of them. Even the earliest cameras, when they were discovered in 1839, the daguerreotype, people were still taking their own pictures. That was the craze. You can have a copper plate, stand there for 30 seconds and take your own nice picture. The Kodak Brownie box is actually very interesting. It's told you that you can do a dry plate and film. We're still talking in late 1800s. And people were taking their pictures by looking in a mirror. So here you see a lady with a big camera in her hand, looking in the mirror and taking her own pictures. That's Stanley Kubrick and so on. So what people have used quite a lot of mirrors to take pictures. That's Stanley Kubrick taking a picture of his own. That's me trying myself in early 2000. And if you think people go crazy lengths to take a picture, here is one picture from 1966 where somebody has gone in a balloon with a camera attached to his foot. So these days we claim that the teenagers go crazy lengths to take selfies. That actually has been there for a very, very long time. So the behavior towards camera is nothing new. It's just that the camera has changed. So much so for the background. Let's jump to electronics. I know Dr. Mighty told that this is all about electronics and computer engineering, and here I'm talking about humanities and history. So let's jump into how do we make a camera. The effect is actually quite simple. We use the photoelectric effect, which you all might remember from your high school physics at the time. Einstein got a Nobel Prize for it. Light falling on a metal leads to an electron ejected from its surface with an energy. And As long as the photon has a minimum energy, it will lead to an ejection of an electron from the surface. If you look at semiconductors, we have got the concepts of band gaps, which you might remember. Insulators have a long band gap, semiconductors have small band gap, or somewhere in between, and metals have band gaps which overlap between the filled and the empty states. So in case of semiconductors, it becomes really interesting. If a light falls on the filled part of the, or what we call as a valence band, as long as it has got enough energy to push an electron from the valence band to the conduction band, it will lead to formation of a current. So light falls on a semiconductor, it leads to a current, and electrically we measure that current. And once the amount of current is going to depend on the amount of number of photons falling on our semiconductor surface. Having said that, remember we talked about photoelectric effect. Each photon has an energy. So at some point, if as the so energy is h lambda or hc by nu, as nu the wave as hc by lambda, as the lambda increases, the energy starts falling down. So for any detector, for any material, it has got the highest amount of energy which it can detect. Fortunately, the wavelength in which silicon responds, in this case, about 400 nanometer to about 1000 nanometer, is also the wavelength in which we as human beings can see. That's the visible spectrum. Blue lies somewhere here, red lies somewhere here, green is in between. So spectral response of silicon very surprisingly matches the spectral response of human eye. Hence we can use silicon as a material to make digital cameras. Now it's also brilliant because silicon is quite widely available. It's available in sand. Sand is silicon dioxide. And in parallel, people were making computer chips from silicon. So we had CMOS to MOS transistors or BJT transistors. They were all being made from silicon. So we already have the processing ability on how to make really small pixels from silicon. So that's the material. We have got agreed on the silicon as the material to make digital cameras because band gap is such that its wavelength, its spectral response matches that of human eye. But this is not how we started. I mean, digital camera technology started with film. Some of you older guys might remember we used to have these photographic films. We used to take pictures and then take the film to a manufacturing place or a processing center, which will be able to record or translate the film onto a piece of paper, what was being called as the developing a film or negative to positive development. Then in about the 1950s, 49, 52, came a technology called charge coupled devices. These were essentially MOSFET capacitors. Light falls on just silicon capacitors. Light falls on silicon, gets converted into charge. We have electron hole pair being stored, and each capacitor stored that charge. And at the end of the frame, we used to move charge from one place to another. Two guys, Boyle and Lusted, they didn't win Nobel Prize for the charge coupled devices, but this is not the technology used to making CMOS cameras anymore. It's still being used for making high-end cameras, but traditionally we actually use something very simple, which is essentially we use an NPN junction diode. Now for those who are not from electronics background or those who might have forgotten based a bit of semiconductor physics, I'm not going through charge coupled devices, but we are looking at a CMOS process. We are using metal oxide semiconductor type of electronic devices, standard MOS transistors. And the reason it's beautiful is that it has diode, and we need a diode to have a photocurrent. We also use diodes in solar panels to generate electrical energy. It has diodes, but it was always very poor optically. But the promises it provided were immense. If you make anything in a CMOS process, the transistor size keeps on reducing. So we can have more pixels, and this is why you can get 50 megapixel, 100 megapixel, and so on and so forth. You will have lower cost, lower power, higher speed, and you can start doing processing. We make our processor and memory from the same process. So why can't, if we make the camera in the same process, then we can put both of them together and we go forward. A quick summary, you might remember that's what a transistor looks like. It has got a source, a drain, a channel. That's the characteristic of a transistor. There's a saturation region where any application of the drain to source voltage, the current pretty much flat lines. And there's a linear region where there's a linear relationship between drain to source current, drain to source current and the drain to source voltage. That's just a basic driver. Essentially, a transistor acts as a voltage controlled current source. If you just remember the basic operation of a MOS transistor, we would be fine. This is how we manufacture. So that's a classical inverter, and you might remember how inverters operate as well. There's an N-type transistor, there's a P-type transistor. We apply a signal here, it gets inverted, we get an output. Thing to see here is this: if you're making the structure, you have N-type MOSFET, N-type silicon structure, a doped silicon structure, and P-type doped structure. And wherever you bring N and P together, you're already forming a diode. And once the diode has been formed, this will be photosensitive, which means any metal oxide silicon structure is photosensitive. We can actually use any transistor, any diode for imaging. We are going to use a reverse bias photodiode. So essentially what we have is we have an array of diodes, and this was from the early digital cameras built way back in the 60s and 70s. Not terribly great, but let's just bear with me. So it was essentially a series of diodes with a switch connected to each one of them. If light falls on each one of these diodes, the photo-generated charge gets stored. And then we go on reading each one of them. So first we switch on this switch. The current from this comes onto this line, and we read the amount of charge there, then we read the amount of charge there, then we read the amount of charge there, so forth and so forth. So it's essentially an array of photodiodes, as simple as that. Now let's try to do some maths. You can't have an electronics lecture without doing some basic computation. So we did talk about the energy of a photon is hc by lambda. Let's take the green wavelength, where it is about 600 nanometer is the wavelength. And if I put the values of Planck's constant and the speed of light, I get the equivalent amount of energy. And then we calculate how many electrons will be there if we have got about a typical size of a diode. We get the photocurrent of the level of about 6 femtoampere. So each site produces 6 femtoampere of current. Femtoampere is 10 to the power minus 15. That is a very, very small amount of current to be read through using long lines. So if we have, say, a megapixel camera, you will have 1,000 rows and 1,000 columns. So this is, and if you're trying to read from the topmost row and column with a very small amount of photocurrent, it's going to take a long period of time. You're still going to charge a capacitor. So the charging time will become very, very large. So we don't use these classical passive pixel sensors, which is an array of diodes anymore. What we use is something called an active pixel sensor. And that's what we're going to start with a diode. So very simple, it has got a photodiode. Then I have got something called a reset switch. So it's another transistor connected on top of this, and this acts as a switch. So either if I switch this transistor on by placing a high voltage, this switch will become on, and this top of signal VRST will come onto my photodiode. If I switch it off, this will be disconnected and this photodiode node will be floating. Then I have got two more transistors connected to the diode. I have got one M2, which actually acts just as a source follower. It's a unity gain amplifier. It's a buffer. It doesn't act as anything else. And then I have got another switch. This switch I use to access to this particular transistor. Remember, if I make a 10 megapixel camera, I need 10 megapixel lines coming out of it. And that's going to be difficult. So I multiplex. I read one by one, just like the way we do in TV. We read the first pixel, second pixel, third pixel, and so on and so forth. So operation is fairly simple. If I measure voltage versus time, I first reset my transistor M1. The signal at N1 becomes very high now. So N1 node becomes high. I switch this M1 on, V reset falls on the diode node, the signal point becomes very high. Then I switch this M1 off. So it's no more connected to V reset signal. Now light falls on the photodiode and light generates photoelectric. Got it? All the electrons move towards this node and they start discharging this node. So if I have a low amount of light, this node discharges slowly. If I have high amount of light, this node discharges very quickly. I read out this voltage after a certain amount of time. Now, that certain amount of time is fairly simple. We as human beings cannot see a video, cannot differentiate between continuous motion of still images as long as they are coming with more than 20 frames per second. That's the limit of human eye. So if I take 20 pictures in a second, I would be recording a video. 20 pictures in a second is 50 milliseconds per picture. So I basically charge this signal for about 50 milliseconds. Once I have done that, I record whatever is the signal at the end of it. That signal is going to be directly proportional to the number of photons falling on my pixel. That is the bottom line of pretty much most of the circuit which is there. So it's one diode, 3 transistors. An operation is fairly straightforward. You reset the diode, let light fall on it, let the diode signal go down. At the end of the frame, you switch your transistor M3 and read out whatever has been stored on N1. That's the pixel. We need something in the column, because if I have got 1000 rows and 1000 columns, if I have just got one line connecting all the pixels in a column, I will still need 1000 output lines. So in the column, we can do something like the same. Now we have got a source follower connection in the column as well. So that's the source follower bias for it. And we have got another source follower. This M5 works as a source follower. Whatever comes on the output line now gets pulled up. I've got a column select line, and we have got enough. So overall, our circuitry looks something like this. I've got a pixel which has got 3 transistors and a diode, and I have got some column lines. So I've got another set of 3 transistors here, one to just provide current for providing bias to the source follower, and another being another pair of source follower and column select lines. So once we select this line, the signal goes on the output, and so on. So that's the basic background of the pixels. Now, if you ever go and make a camera with this 3 transistors and a diode, you'll end up with an image something like part A. You'll end up with a very, very noisy image. So that is an image of something which we recorded in our lab, and you can see it's not really very good. I mean, the image B is much better when it has been processed properly. But what the image which you record with any digital camera is actually quite noisy. Now, there are 2 types of noise which you might have noticed. There are these stripes. There are these vertical lines going down. And they are an interesting thing, because essentially they are telling you that we have got some noise which is correlated to one another. So every pixel in one column has one noise, and every pixel in the other column has got another source of noise. So at this point, let's go back to semiconductor physics and see where exactly our noise are coming from. What is the origin of these noise, and how they degrade the performance of our camera. I'll take a break here for a minute and just drink a bit of water, and we'll be back. So till now we have talked about image sensors, how the basic circuitry operate. It's a 3 transistor in a diode, but we still capture very poor quality images. Good. So let's talk about noise. Now, all of you guys would have taught noise to our students and have also studied noise in your various electronics courses. There are different types of noise, and they affect different performance. Now, we're not going to discuss the background of noise. We're just going to remember what type of noise there are. So first noise which I have written is the one which I cannot do anything about. This is the short noise. So short noise is because all our electrical circuit or photonic circuits have got there are discrete charge carriers. So when light falls on a structure, it has got a large number of photons coming in. And photons are not a continuous wave. They are also waves, but they also act as a discrete elements. So they are quantized particles. Now suppose when I say that X amount of light is falling on my camera, which relates to a Y number of photons. So per second, I need Y number of photons to come there. Now, photons are very much like your students. They never come to class on the same time. There's always a delay. So some students come early, some students come late. And this leads to kind of a noise, which is called as the photon short noise. So because things are not coming exactly at the same time. Now, photon short noise is the fundamental limit of imaging. You cannot do better than the noise provided by nature. So photon short noise is there in nature. We also have the DC current short noise. Remember, current is flowing in all of these structures. Source follower, there's electrical current flowing. The output line, there's electrical current flowing. This is again a flow of finite number of electrons, which are quantized, which means that the amount of electrons coming at one node is never constant, which leads to another sort of noise. The third is the thermal noise. Now, generally we teach thermal noise first. This is the noise which comes out in resistors and gets stored in capacitors. But I've talked in the last because that is a bigger noise which we need to worry about. That's the killer noise in our operation. Because what we are doing is the light is falling on our diode acting as a capacitor in this case, and it's getting stored on the capacitor. Now, the storage leads to reset noise, and then we reset the whole thing, right? We switch on a switch. The switch starts acting as a very low resistor, which in turn produces noise which gets stored on our capacitor. So it becomes a very noisy operation. So our task then is to reduce this amount of noise, because our end customer will not buy a poor quality image. And some of the early digital cameras which were very popular in the market were the cameras which were placed in toys, because elder customers wanted very good quality images. Our younger customers, 5-year-old girl taking a picture of her daddy, they were perfectly happy with poor quality images. So whatever you give, they were happy with. So the noise is a killer. Now, but that's not the only source of noise. If we go back to the operation of our circuitry, what you might find is that each pixel has got transistors. But what we want to do is we want to record light. And the light recording part is our photodiode. So in this case, what we would like to do is we would like to, I've got a chat. We would like to ensure that the diode is as big as possible to capture as much light as possible, which means these transistors have to be fairly small. Now, just like in nature, no two human beings are completely identical. No two transistors are completely identical. But the problem is, the smaller you make the transistor, more is this non-idealness which is differentiated between them. So if you have smaller transistors, they are different to one another by further amount. Now we try to make really small transistors, which means the response of each pixel is going to be different. Even if you take a picture of white light, they are going to be quite different. So there is our noise flow. We take the reset transistor adds some noise. The photodiode adds some noise, because again, not every two photodiodes are going to have different response to each pixel. We have got flicker noise, we have got quantization noise when we translate the whole thing to an ADC. So we get quite a lot of noise sources in this whole chain. Fortunately for us, there is one very simple solution to this whole thing, and that's this circuit. So here what we do, now remember I told you what we do in our pixels is we actually reset it and then we allow it to discharge. But while it's discharging, the diode is not connected to any resistor, so there is no new source of white noise, thermal noise, thermal and white noise. So if we could record the reset point and the integrated point and take the difference between these two, that will give us a noise-free image. So what we have done is we have just changed the diode such that there is a big diode, this ED, and there's something called a floating diffusion. There's a small capacitor in the pixel connected by a gate type switch. It's not a MOSFET, but it acts as a switch. And by having an internal memory in the pixel, we actually can take both the reset value as well as the integrated value. By doing this, we will be able to remove all the fixed pattern noise as well as temporal noise, or most of it, not all of it. There's quite a lot of noise left, but in generally, by doing this kind of a 4 transistor approach, we get very good quality operation. Now, you can have further column circuits to reduce further noise. I will not go into detail into this. We'll go into this stage. So now we have made a pixel. But our end customer is not going to buy pixels. He wants cameras. He wants a very large number of pixels. But more importantly, the rest of the world is digital. Our pixel is going to produce an analog output. So how do we translate an analog output to a digital output? And where do we do that? So one solution could be do like we do in memory or in TVs. We have got a series of shift registers on the row, a series of shift registers on the column. We have got an arrays of diode or detectors or active pixel sensors, and we first read the first one, then we read the second one, then we read the third one, fourth one, so forth, and then the second column. And once we have read all of it, we put a very large analog to digital converter at the end of it and convert it outside. The problem of doing this is it works very well when you have a small number of pixels. But let's do a simple calculation. Now I've got a megapixel camera, which means 1000 rows, 1000 column, and I need to record 20 frames per second. So I have got 20 megapixel of data. Each pixel I will generally use 8 bits at least. That becomes 160 megasamples per second. This ADC is going to be quite power hungry just for 1 megapixel. Now if I place about say 100 megapixel, I'm already talking about 1.8 gigabits per second on a single chip. The amount of power required with this ADC is going to be a huge one. So hence, it's not really doable. We will look into the kind of ADCs we choose. So rather than placing an ADC just at the column at the end of the image sensor, we then go and place an ADC in each one of these columns. So for every 1000 pixel, every 2000 pixel, we have got one ADC. So if we have a 1000 column structure, we will end up with 1000 ADCs per column. The question, of course, then it raises is what type of ADC should we have in our system? So the simplest ADC we can think of is going to be a flash ADC, something fairly standardly taught in all courses. It's very fast, but A, it's power hungry, it takes a lot of power. B, it's actually quite area intensive. So if you say you're making an 8-bit flash, you would need 256 comparators. If you're going to place 256 comparator per column, our chip is going to become very, very large. And we can't afford a very large chip because we have to put it in a mobile camera. So the ADC for choice in most, well, a large number of digital cameras is something called a ramp ADC. So ramp ADC works very simple. It has got a one comparator. The input signal comes in, and then on the other side of the comparator, we place an increasing ramp signal. So it's an upward going signal. And we just keep on comparing. And we also have in parallel a counter going. So we're counting 1, 2, 3, 4, 5 till 256. And the moment our ramp value is more than the value which is at the input of the comparator, the comparator flips and we stop recording anymore. So we stop that value of the counter. So if the comparator flips at 128, we say 128 was the ramp signal, was the input ADC performance. So overall, our signal then starts looking something like this. So that's our 40 pixel. We have got 4 transistors, a diode, and we have got a ramp converter in each column. In the ramp converter, essentially we have got a comparator, we have got a ramp signal generator. We generally integrate a current on a capacitance to produce a signal generator, and then we have a counter and a control logic. This is as simple as that. We take that ADC and then go and place in bottom of each column. And that pretty much does the job for most applications. But if you really want a very high speed, high number of pixel operation, even this actually does not do a very good job. Now you have to move the ADC from each column to one ADC per pixel. And anyone who has designed an analog to digital converter will tell you that this is not an easy task to undertake. Now, the size of the pixel is actually fairly small. So if you want 100 megapixel on a small 3mm by 3mm chip, the size of the pixel is going to be lower than 1 micrometer. Now, in a size smaller than 1 micrometer, you try to design an ADC, it's going to be very, very challenging, if not completely impossible. So either increase the size of the pixel and hence reduce the number of overall pixel in your chip, or you don't impose such criterion. So sometimes we also place a bank of ADC at the bottom and another bank of ADC on top of the image sensors. So as an overall comparison, this is how our ADC would look like. We have got fairly complex circuitry in the ADC where we are not even showing the SRAM, the memory elements. So that's our fairly complex comparator. So you can see the number of transistors going up quite a lot, but not so much in the pixel. In the pixel, we are still having just a 3 transistor and a diode. It's our column structures which are becoming more critical. That's the design part of it. But remember, we also have to make these things. And to make these things, we need to give a layout to our end customer, which is the foundry which is going to fabricate these things. So a typical layout of a image sensor or a pixel is going to look like this. We are going to have a large photodiode to collect light. The larger the photodiode, the better it is. And then we are going to place our reset switch, our row selector, our source follower, and other things on top of it. Sometimes to increase the area even more, what we do is we've shared these reset and transfer gate switches. So we might have many diodes one after another, and we share these diodes to a reset line. So reset, source follower, and everything are shared. So you might hear 1.5 pixel or 1.75 transistors per pixel. So now we have 4 pixels, each with their own diode, but now we have shared the reset row select lines together. So we are getting less number of transistors. By having less number of transistors, we are increasing the size of the photodiode. Good. So much so for making a pixel. We have got a fairly standard 4 transistor pixel, fairly simple layout, and we are done. But now our end customer wants a color image. He or she is not happy with black and white. So how do we create a color image out of it? Silicon has response to all spectrum. It responds to everything from blue to red, which means it generally produces a black and white image. In order to produce color, we actually put a color filter mosaic on top of the pixel. And we call it a Bayer pattern. So we would distribute a structure something like this, where we would have double the number of green. So you can see there's a green here and the green opposite to it, and then we'll have blue and red. We use less number of blue and red compared to number of green because human eye is more sensitive to green. So we capture more green light than red and blue. And then we do demosaicing. We do some sort of mathematical operation to say, okay, I've recorded green here, but I don't know what is the value of red and blue here. But I do know the value of red across B. So I take the average of these 2 values to become the red here. Or if I take the average of blue values from these 2 to become the value of blue here. So I can do demosaicing operation to improve the performance of my color filter. But in a sense, we use a series of color filters to get color image out of it. Very much like the human eye does, which has red cones, blue cones, and green cones to take different spectrum of visible spectrum. That's all right. Till now, we have produced a camera, we have produced a color image. It's still not very good. And if you try to take pictures in very bright daylight, like for example, this is a picture of McGill University. If it's very bright daylight, we either take with the sun, the sky, or we can have more information in the lower part. But when you have more information in this say the building part, we lose the sky information. The sky becomes completely white. We call it saturated. And if you have a very bright sunny day outside, you might see where your mobile phones take very poor quality images there. Or if you have very high speed moving scenes. So this was a scene of a airplane rotor moving around. Actually, this was taken in Lilabari in Assam, so not very far from where you guys are. If you have a very high speed moving scenes, our cameras also fail, because by the time we have reached here, the scene has already moved. So rather than discussing on how do we do to improve all of these characteristics, I will just discuss the first problem, which is how do we take images which can record very nice quality data at low light as well as at very bright light. So to understand this, we will go back to why we are not able to take high quality images. So why does our camera saturate? Why does it not take good images when the light is low? Remember, right from the early days when we started talking, light falling on the diode discharges this reset value. Excuse me. And at this discharges, if the light is too high, it discharges to almost zero and saturates there. You cannot go below zero because there is no power supply to provide current for it. So the signal is lost in this structure. So one way to do that is, why do we wait till here to record the signal? If we take another value right here, we might be able to record this high signal. But if we record the value here, the low light would produce very, very small signal, or it will be noisy signals. We will not be able to differentiate the low light. Solution? Okay, take one picture here, take one picture here. So if you take two pictures, one at small integration time, one at large integration time, you will be able to record very wide dynamic range of responses. And that is actually a very old technique. When United States tested their nuclear weapon just during the World War, just before the Second World War and the end of the Second World War, you needed to take pictures of this really bright scene which was happening. And one way to do that was to use this, take the same picture but with different integration time and record that. You might immediately say, it's fine, if you take different integration time, what's going to happen of noise? What's going to happen here? It's going to be quite noisy. And that is indeed true. If you look at the surface signal to noise ratio, we get this noise jump. So the light intensity, as it keeps on increasing, we get a certain signal, and then we fall down and then take another signal. So there's quite a lot of noise between the frames. But more importantly, we also need memory. We need to store 2 or 3 pictures per picture being taken. So it increases the computational overload later on. So you get more noise, you get more fixed pattern noise, and now you require more memory inside these pixels. Solution? Why just stop at 2? Take many images, take 3, 4, 5 images, and then use some sort of mosaicing scheme to improve your image quality by doing this multiple image capture. And this has been done. People, when you buy a digital camera off your mobile phone, it has got something like HDR or WDR written for high dynamic range and wide dynamic range. Most of the time, they are doing some sort of double sampling or multiple sampling. They're taking the same picture at high frame rate at multiple times, and then doing computational processing to get one good image out of it. An alternative is to do something like this. Remember, we had 3 transistors in a pixel. So rather than using your transistor M1 for resetting, you can use it in its subthreshold region of operation. So we make it work as a diode. Now, when you have a diode and a small amount of current, the relationship of the voltage to current is a logarithmic relationship, or it's an exponential relationship. When we teach in our school, I is equal to e to the power V, where V is the voltage applied across diode, which means the voltage is log of I. So if we get a large range of photocurrents being produced, small amount of photocurrent for low light, high amount of photocurrent for high light, one thing you can do is you can put a logarithmic amplifier inside the pixel and compress the whole of it. So now you can get a smooth, wide dynamic range response. The problem of doing logarithmic conversion is the signal gain also is logarithmically converted. So the signal range is converted, So say if you could, earlier you could only record between one input, one unit, in this case we'll use lux as the input, between 1 lux and 1000 lux. Now you can go from 1 lux to say 10 to the power 6 lux. But the voltage swing is still the same. You're still recording between 0 and 3.3 volt. Actually, in log pixels, you only have 600 millivolt to record this whole swing. So in 600 millivolt, you are having 10 to the power 6 levels, which means the resolution, the light resolution becomes quite small. So gain is low, you get much more noise in these signals. So even though it's a very good quality, market penetration of this technique has been fairly limited. I'm not going to talk about the other end because I'm aware of the time already reaching at the peak of 1 hour. So we talked about the higher end. So how do we improve the image quality when you have got very bright light? How do we improve the image quality when we have quite low light? In order to understand low light, we need to see why our pixels do not operate when there is low light. Now, when there is low light, there is a small number of photons falling on the pixel. But in parallel, something also happens that the small number of photons have to fight with thermally generated charge carriers. Now, if you take a diode by itself, it will always produce a noise current. And the noise comes because we have some thermal drift current, we have leakage currents on the surface, we have got leakage currents on the side, and you guys would have taught about the thermal generation recombination current, which is fairly first thing we teach in diode as to how at different temperature we have got different diode current being produced. All of these currents are already there. So these produce leakage current, what we also call as the dark current. So even when no light falls on our diode, it produces a current. Now, unless the current produced by light is more than the current produced by this noise, we will not be able to record that. So how do we improve this? We can go and improve our process. We know where this is taking place. We know it's taking place because of leakage on the surface, because our surface is not very smooth. So we can use some sort of a high temperature process. We can reduce the surface defects by some separation of the techniques. We can improve our shallow trench isolation or use a P-well type separation. We can use deuterium, which is a high H2. We can use that for annealing the surface. There are various techniques which we can reduce the dark current, but they come at a cost. More is the manufacturing thing we apply, higher becomes the cost of your camera. So we talked about the various ingredients to making a camera, but on top of that, we now need to worry about how do we design an image sensor. We have got the pixel, so we have to first determine how many number of pixels we are going to put in our camera. What's going to be the size of the sensor? So if it's a fairly standard size, or we can have a larger size. Sometimes when you are using X-ray imaging, you have got films which are as big as a computer screen. So the size of the sensor is going to determine the size of the pixel. Pixels are now fairly standardized, so our job is then to create an array of pixels, design scanners from both sides. Once you have designed that, you have to design or select the data converter. How are you going to convert data from analog to digital, from an analog output of the pixel to a digital output? Design the data converter. Place the data converter in each column, or 2 in each column, or if you are forced to place in the pixel, but I can advise against that. Design your color filter. You need a red, blue, and green color filter. Sometimes people also use more than red, blue, and green. If you want better color contrast, we could end up with red, blue, green, and white, or red, blue, green, and infrared, or further combinations of these. Take the data output from the sensor, and then you have to do quite a lot of digital processing. You might have to extract color, or you will have to extract color. You might have to improve the noise performance of this signal, and you may have to do further image processing. So once the image is acquired, what do you do of an image? You either store the image or send the image for further recording somewhere else, or you try to do it meaningful. For example, if you're making a security camera, you might ask, okay, How do we extract information like, is a human being walking? Is the human being walking in my scene? Is the person of interest to me? So all of this image processing comes next to it. So we do some early image processing, which is color extraction and noise correction. And then there's a late image processing, which you have to do on a digital camera or digital computer or in the cloud somewhere else. So that, my dear friend, is the whole background about how to design a CMOS image sensor. What are the various considerations required? I believe I have got about 4 or 5 minutes left in an hour, so I'll be happy to take questions at this point of time, or you can send an email to me if anyone wants to know any further. Thank you very much, and over to you, Dr. Maiti.
Thank you, sir. It was a very outstanding lecture, I can say. And we know everybody, I think all are near about electronics background, so we know that it was a now CMOS image sensor is one of the hot topics in the research, and we have transformed from CCD charge coupled device to the CMOS image sensor due to some there are lots of advantages. Thank you very much, sir. We have known different how to design dark current as well as some human eye versus digital camera. That type of comparative also we have seen in your slide. It was a very very what I will tell, very important for us also. And now I can request some participants, please ask the question, and you can write in the chat box then I can take it out this question, or sir can directly also take it out from there also. So please give some questions if you have. I'm requesting to all participants.
If I have not put you on sleep already. Excuse me. I have a question from Suparna Panchanan, if I'm pronouncing your name correctly. Is there any advantage of gallium arsenide over silicon? Yes and no. It's a classic diplomatic answer whenever somebody asks about gallium arsenide. So the band gap of gallium arsenide allows you to go further in infrared region. So silicon by itself has very poor response in infrared. After 800 nanometer, its spectral response starts falling down. Gallium arsenide is very good. Actually, if you impose something else like aluminium or indium on it, then its performance, you can tune its performance to work in infrared. So you can take the heat maps, you can make thermal cameras out of it. The poor part, it's costly. Unlike silicon, it's not as cheap. Silicon is used for making a large number of other chips, and gallium arsenide is not, which means if you're just making a foundry for making a gallium arsenide camera, the camera is going to be very costly. Right now we sell cameras for about $5 US. You might have to sell for $500 US, no one will buy that. But in the infrared community, yes, gallium arsenide is a very good thing if you want to make cameras. Now, if I might ask you, what are infrared cameras used for? I mean, okay, there is something these days. If you're looking at people who have got coronavirus, the first thing you do is you measure their temperature, and you can use a thermal camera for remote measurement of their temperature. But a much wider application of thermal cameras is in the defense field. Unfortunately, you don't talk about defense cameras in public domain because most of the defense cameras are export controlled. So if anyone is looking, I mean, if you want a remote camera to operate, say, in the mountains of Himalayas, then of course, and you want to just look at the thermal heat map, you want to see if somebody is walking through this one big screen of white snow. In that case, you would be making a camera made of gallium arsenide. Or if you want to look at the heat map from the desert, again, you will be using gallium arsenide or various alloys of gallium arsenide. So yes and no being the answer, but integration as a chip, as an image sensor is fairly difficult with gallium arsenide. I hope that answers your question.
So, is there any question from participant? Please tell me.
Sir, actually, I have one question just for my means curiosity. That is it possible to means make our eye means artificial eye?
Ah. So the amount of research which has gone into making artificial eye is huge. Actually, when I was doing my PhD, and my PhD was on reducing the fixed pattern noise in digital cameras. Remember, I showed you noisy images. I asked the question, we don't see noise from human eye. I mean, you were reading a speech, it's not a noisy image, right? The human eye should have a very good correction scheme because the pixel in the human eye is quite small, smaller than our pixel. So it should have quantum noise. I mean, you can't do anything about quantum noise. Has to be photon shock noise. But the human eye somehow corrects for it, which means there has to be a very good correction scheme. If only I could go to a psychology school and learn. So this is why I suspended my PhD and went to Max Planck Institute of Brain Research to learn how the human eye works so that I can go back and make the best camera in the world. Slight problem there. We don't know how the human eye works. So irrespective of what the ophthalmologist or neurologist tell you, our sheer understanding of how the human eye operates is less than 1% of its operation. I mean, I'll give you a very simple example. We have 125 megapixel in our human eye. From there, only 10,000 neurons or 10,000 lines go to our human brain. So the visual part is in the back of our head. So from our eye to our back of the head, 10,000 lines go. Now all of you are electrical engineers. Try to record 125 megasample signal with 10,000 lines and uniquely map. We don't differentiate between this. So our human being already starts with, our human eye starts quite a lot of processing. We don't even know how the processing happens. We're at very early stage of it. So we don't know how the human eye works. But blindness is a big issue. Loss of eyesight is a big issue. So people have worked on different aspects. Okay, we can't get a perfect eye. Can we do something better? So people looked at implantable eyes, and that idea was very quickly thrown out. Because anything which is implantable and is like a human eye, it's constantly working, will require a lot of power. Right? So the solution then was, okay, can we put a camera on top of it? So you wear a glass, you put a camera on top of the glasses, and you send wireless signal back to the end of your retina. By doing this, so the camera is in front, you can attach a battery to it. Only thing which you are sending is electromagnetic stimulus to your retina. By now, there are techniques where we can see edges. So completely blind people can see that there is a shade of blue, there is a shade of black and shade of white. There are edges in the screen, but they're not necessarily, we do not know necessarily as to, we can't take a picture as yet. Because we can't take a picture, but we don't know how to transmit this picture to the brain. This brain will be, so unless you replace the whole brain, it's still an area of active interest. To give you the full answer, when I told to my PhD supervisor many, many years ago that I'm going to study the human eye for next year, he said, well, you'll be studying the human eye for next 50 years and you will still not know the answer. So I'm pretty sure we'll be studying for a lot of time before we understand where the human eye is going to be. Not yet. Wait for it. I hope that answers your question.
Yes, sir. Thank you, sir. Thank you very much. Means I always used to think that we talk about sensing technology, sensors, but human body is the best sensors. We have
no, human body is not the best sensor. I will argue against that. Okay. It's a very good sensor.
Okay. Okay.
The reason why it's not a very good sensor, okay, let's take an argument. I mean, I always say if you believe in God, he was a very bad designer, he or she. The design has not been very good. I mean, think of it this way. So let's take a sensing operation for human eye. It takes a long time to mature. So you buy a human eye, which is a child born, and it takes 5 years at least. I mean, at least take 3 months for the child to differentiate colors. So newborn child can only see till about this distance, right? And they basically see hazy structure. So this is why we take children in our laps and try to shake them so that they see movement If they don't see movement, it saturates immediately. So it takes about 3 to 4 months for the camera to just learn there's red, blue and green color. Now, if I sell you a camera today and tell you, by the way, Mr. Dr. Ghosh, it will take you 4 months for this camera to learn. Just keep on teaching it every day, 24 hours. You will just throw the product away. I'm not going to buy that product, right? So the camera is good when it matures and it learns. It learns over a period of time. Our digital cameras don't have the luxury of learning. We need to sell them as they are. They should be able to capture information and extract information. Having said that, with this learning, the human eye does very well. Once it has learned, it takes quite a lot of low power. It's not very high speed. I mean, we can fool the camera eye, right? You are seeing a video of me by fooling your human eye. We're just throwing 20 pictures one after another to you. And the human eye cannot differentiate. So it's not a terribly great camera. The other thing which happens with the human eye is it degrades in performance. I mean, I will be needing glasses very soon. So if I send you a camera today, oh, by the way, Dr. Ghosh, he has a very good camera. In about 5 years, you need to put glasses on top of it and keep on changing the glasses every few years. That's not going to happen. So yes, there are some good aspects of the human design, but certainly not the, the best camera I would say would be in the insects. We can see 360 degree. Our human eyes can't see 360 degree. We actually can only see in the front. And on the side view, we can barely see motions. If you move your hand, you can figure out a hand is moving, but you can't see what is moving. Again, it comes from evolution. When we're evolving, we needed to see a tiger coming at us or any animal coming at us. We knew all animals will kill us. We were the least powerful animal in the forest. So any motions, our eyes were adapted or evolved to see any motion. So in the front of our scene, we can see everything. On the side, we can just see motion. So yes, they're good, but I still believe we can make better, but give us some time.
Okay. Thank you.
Sir, we have got two questions. What is bionic eye?
Of course, I was talking to you about artificial eyes. I mean, bionic eye has been a buzzword which has been thrown about in the community before I was born. The whole idea is that we will have a robot which will be able to capture the image as well as understand the image. Is a bit of fantasy right now because yes, we can capture images. The image understanding part is actually quite difficult. To give you an example, you guys might have heard of the Google Brain project, which was the first result for convolutional neural networks. What the Google Brain project's first result, I think it was published in 2005 or 6, they were able to identify a cat in YouTube videos. So you can show any YouTube video to the Google Brain software and it will tell you whether there is a cat in the video or not. To do that, it required 10,000 processors and 100 kilowatts of power. Just to identify cat, no dog, no human being, just cat. My 5-year-old son can identify a cat in YouTube video on a slice of bread. That's what I feed him in the morning, and it can still identify a cat. So the bionic part is the understanding of images very slow right now. I mean, even though we have got automated techniques, we're essentially throwing big GPUs and data servers to extract information out of an image. I mean, you might see we put CCTV cameras and you might say, okay, if the CCTV camera is placed, why can't the police catch the thief? Because you still need a human being to go through the whole chain of scene. So if you have a 24-hour camera, you need somebody to look at the scene for 24 hours to identify information. So the bionic eye capture part is ready. Image understanding part, now that's a very difficult and very open question. So in research world, people are looking at robotic vision. Machine vision is a very big community, but these are at very early stages of image understanding compared to what animal vision does.
I think another question we have received that can I use wave sensor in drone?
Now we'll then have to ask, how do you define wave sensor? Are you looking at electromagnetic sensors or are you looking at audio sensors? So there are different kind of wave sensors, right? I mean, when you have a digital camera, that is actually a wave sensor, right? It's recording electromagnetic wave. Then there are people who make radars. They are a kind of a different wave sensor. So there you basically send a wave and receive the wave back. There are people who do 3D imaging. And the way you do 3D imaging, you send a laser beam or an audio beam out, and when the laser goes up, hits an object, comes back, and then you record the time of flight it has taken, how long it took to go there and come back, and you design a 3D camera out of it. So that kind of wave sensors, of course, you can use in a drone. The bigger problem is not its integration in drone, is the power requirement. Your drones need quite a lot of battery to keep on flying, and you can barely fly them for an hour. If you now are saying, okay, I'm also going to produce an electromagnetic wave, send it and capture. So capturing part is not very power hungry. It's a passive system. The wave goes, comes back, or there is a wave flowing in the nature. I mean, there's a radio wave or TV wave in the nature, and we record that. That's not very difficult. The production of wave is actually still quite power hungry. So that will take quite a lot of power from you. I hope it answers your question.
I think no question, and till now there is no question.
That's good.
So sir, thank you, sir. Actually, I can say many thanks, because when I approached to the sir by a mail, he has agreed within 1 day. So I was that I am also thinking, I was also very shocked that how sir has, he is a very, very good person. Otherwise, he cannot accept within a mail. So sir, thank you very much, and we have received lots of inputs, and in future also we can I can say in future also I can contact, and if you have told me that why not physically, you have asked by phone also, so I want to go with the physical. Sir, it is in my mind, if in this situation will over, and also something its normal position will come, so I will try to approach you again to physically you come to our Mizoram University, and also you see here environment, and also you can get some here also, that just that environmental, we can say that Northeast Switzerland, we are telling sometimes this place. So it is a very nice place, you can visit here. So thank you, and officially thank you giving by the Dr. A. Ghosh.
Thanks, Dr. Maiti, and I wish you all luck in the organization of this development program.
Okay, thank you.
So at the end, I want to give a big thank to Professor Bhaskar Choubey, sir. In spite of his busy schedule, and as we have seen, his health is not, that means, very good. So in spite of all this limitation, he enriched our knowledge in the CMOS image sensors, and hopefully all the participants got some knowledge and some more information in the what is going on currently in the image sensor research field. So we are extremely thankful to you, sir, for joining us on this 5 days FDP program. Along with that, I want to thank all the participants. Without the participant, no workshop or nothing can be success. So I thank to all of you, and hopefully this is today's last session. Tomorrow we'll meet at 10:30 sharp for our technical session 3. Thank you very much, sir.
Okay.